Hello and welcome back to my channel. Today we will be talking about gravitational force near the surface of the Earth. So when we're talking about gravitational force near the surface of the Earth, there's a few things that we can consider when we're doing these questions. One of the things that we can consider is something called free fall. Now what is free fall? Well, this can be understood as when an object only experiences gravity and no other force. This isn't really common in real life because if an object falls in real life, there's often wind resistance or there's wind pushing on the object, and there's obviously other forces that are being applied to the object. Um, and air resistance really prevents an object from free falling. But in this course, we will focus only on objects that are free falling when we're discussing forces, really. So, something we're also going to talk about really briefly is just mass. What is mass? Well, mass is gravity of matter in an object. Mass is actually different from weight because mass is gravity of an object, gravity of matter in an object, whereas weight is the force of gravity acting on an object. So there is terminology wise, they have differences. So when we write weight, that is understood as force of gravity on an object. So now that we have some of those terms out of the way, again, if we're talking about what units we might use for mass and weight, typically we use kilogram, gram, typical weight units that we'd use. And again, because we're still dealing with gravitational force, that's the main topic of what we're going to talk about today. When we're talking about gravitational force, we're talking about Fg, and the units for those are always newtons. And force of gravity is always a vector towards Earth. It's really a constant. Fg is just equal to g, which is equal to 9.80 meters per second squared. Anywhere on Earth, the force of gravity will always be 9.8 meters per second squared. And it's just a constant that we have to keep in mind of when we're dealing with questions, especially if we have an object maybe free falling down here. It will have a force of gravity, which we can interpret as just being 9.80 meters per second squared. The force of gravity also has a reactionary force, which is the force normal. So that's also just something we have to keep in mind when we're working with these things on planet Earth. Because the constant of gravity is only on Earth, the constant of gravity that you might face on Mars will be different. And maybe in some questions you might have to try to figure out what gravity is on these planets. But that's just about algebraic manipulation. And we know Fg is always equal to just mass times gravity. So mass times 9.80 meters per second squared. Fg is really equal to mass times gravity because we have the object, because you have the mass of the object, and we just multiply by gravity, which is a constant. Okay, now that we understand that, we can move on to this practice problem and just practice these skills that we've learned. So let's begin. A 50-kilogram person is standing on a bathroom scale inside an elevator. The scale is calibrated in newtons. What is the reading on the scale when the elevator is accelerating up at 2.2 meters per second squared? So let's try to figure this out with our given. So we already have a direction, right? We have up as positive. So I already know that I'm going to need gravity because gravity is going to be involved in this. Because I want my gravity to be positive, I'm just going to make mine down positive, which means my acceleration upwards is going to be negative 2.2 meters per second squared. It doesn't really matter which one you make positive or negative. Your answer should still work out. Now we also know that they have a mass of 50 kilograms. And what are we looking for? Required to find. It says, what is a reading on the scale? So it doesn't clearly tell us we're looking for this. So let's try to just draw a full body diagram to better understand what we're really looking for here. So we have a force of gravity on the object, but because we need a reactionary force, an opposite force, we have a force normal up as well, because no forces happen in odd numbers. So now that we have that other force, we know that it's going to be, the force of gravity is always happening, but the reading on the scale is going to be the force normal, or the other opposing force, not the force of gravity. Because the reading on the scale is what you push up, right? The scale is pushing up on you, so that's the force that you're going to see on the scale. Because you're pushing down on the scale is pushing up. But in this case, the force of gravity is on you, and the force normal is what's displayed. But regardless, now we can know that we're looking for force normal. So we can use our vectors right away. And we can go F is just equal to Fn plus Fg. However, in this case, because we do just want to interpret our direction and just not use vectors, we can just automatically just put in our direction. You don't have to do it this way, but I just prefer putting in directions right away. So we can just go F net is just equal to, or F is equal to Fg minus Fn. And we also know F is already equal to m times a, mass times acceleration. Now that we know this, we can just sub in that for F. So we can go m times a is equal to Fg minus Fn. And we want to get Fn by itself. So to do that, we can rearrange this equation. We just do plus Fn minus ma. Now we have Fn is equal to Fg minus, minus ma. Now that we have this equation, we're all done. So really, the key part of this question was really trying to figure out what we're looking for. We were really looking for Fn because that's the opposing force to the force of gravity. And because we're going up, we just have to set some things as negative, and we're just going to be using Fg. Again, the thing that made this really easy and really quick was this full body diagram. Because we had the full body diagram here, our whole forces were labeled out for us, and we knew we already had Fg, and we were looking for Fn. So it was really easy for us to find what we're looking for. Also, remember that Fg is always equal to m times g, like I stated before. But let's continue. So we have Fn. We can just go into our solution now, actually. We know Fn is going to be equal to Fg, which is just going to be 50 kilograms times 9.80 meters per second squared minus 50 kilograms again times negative, because remember we set down as positive, so up will be negatives, times negative 2.2 meters per second squared. Now if you punch this all into your calculator, what will happen is you'll get a negative number here, and that ends up becoming positive, because a negative with a negative just creates a positive, and you should end up with 600 newtons as your final answer. I hope you enjoyed the video, and you remembered to always use your free body diagrams, especially in questions like these. Your free body diagrams in all forces are really useful because they help set a basis for what you're really looking for. So make sure you use free body diagrams in your homework and fun work, and you will be successful throughout this unit. So I hope you enjoyed this video, and next video we will be talking about forces of friction.